Welcome to Algebra 2, Module 1, Linear Functions and Equations. Our first lesson is on graphs of lines. There's two forms we're going to focus on. The first one is slope-intercept form. What you need to know for that form is the slope and the y-intercept. The slope and the y-intercept. So if we were going to graph the line y equals negative 3/2 x plus 5, we would say that the slope is negative 3/2 and the y-intercept is 5. We're always going to begin at the b, the y-intercept. We're going to begin on the y-axis at 0, 5, and then from there we're going to slope negative 3/2. So remember, that's rise over runs. The negative means that we're going down. So a rise of down 3, right 2, down 3, right 2, down 3, right 2. And if you had room, you could do left 2, up 3, just to continue that trend. And that is the graph of that line. The other form that's pretty common is called point slope form. It again has the slope in there like before, but this time instead of a y-intercept, it just has a random point. So it has a random x and a y value, and they're positioned right there. So on this first example, we've got a slope of 2. We could think of that as 2/1 for our rise over run purposes. Now the tricky part is for that point. We know that this is going to be where our x1 comes from, and this is where our y1 comes from. But they're going to look opposite, meaning that if you see a +1 over here, that means that your point is at -1. And if you see a -3 right here, your point is at +3. So that's one thing you'll want to watch out for. But if you can pick out your point and go ahead and graph it, -1, 3, from that point now, you're going to start doing the slope. So in this case, it was 2 or 2/1. We're going to go up 2, right 1, up 2, right 1, which would be the same thing as down 2, left 1, down 2, left 1. Get enough points on there so that you can see what that line looks like. Lesson 2 is for slopes of lines. We're going to use the slope formula. It just calculates that rise over the run. You find the rise by subtracting the y's, and you find the run by subtracting the x's, because up and down is y, and left or right where you run is x. We're going to find the slope of the line passing through the points 4, -5, and -2, 5. So when I look at this, I think of this as x and y and x and y. Which point you think of as the first point and the second point doesn't really matter, but I usually just say that's the order I go in. So when I do my formula, I'm going to take y2 minus y1 over x2 minus x1. I'm getting 10 over -6. Go ahead and simplify that. -5/3. Let's look at that on the graph and just make sure it looks right. So we've got 4, -5, and -2, 5. And that's the line we'd be thinking of. Let's just check if that -5/3 looks right now. So we're going to go down 5 over 3. We're right on the line. Down 5 over 3, right on the line. So I think that's the correct slope. If we wanted to make another line that was parallel to that, maybe a line like this, what kind of slope would that line have? That line is slanting exactly the same, so it should have the same slope. So also a -5/3. Now let's think about a perpendicular line. Let's say we were going like this. If we wanted to be perpendicular to the orange line, well, in that case, when we slope, we're actually going to go up 3, right 5. I didn't draw it perfectly. The thing to remember there being that perpendicular has the opposite reciprocal slope. That means we're going to flip the fraction and negify it, or if it was already negative, it'll become positive. So this one will have a slope of up 3 over 5. So -5/3 and 3/5 are two perpendicular slopes. What if you do this whole formula thing and you come out with a 0? Say you have a 0 on the bottom or you have a 0 on the top. How do you answer that? What is the answer then? So one thing that I use to remember is it is okay to have a 0 on the top. It is a no-no to have a 0 on the bottom. See how that looks like a 0 and that looks like a 0? A 0 on the top is okay. A 0 on the bottom is a no. So when you see a 6 over 0, you can't do 6 divided by 0. You get an error. We call that an undefined slope. Doesn't mean that there is no line, it just means that the slope is undefined. So if we started at a point and we went up 6 over 0, up 6 over 0, it's just going to be a vertical line. And a vertical line sort of has a slope of infinity. So we would say that that slope is undefined because infinity is not a real number. If we started at a random point and we went up 0 over 4, up 0 over 4, we call that's a horizontal line, and we call that slope a slope of 0 because 0 divided by 4 is 0. Lesson 3, writing equations for lines. We're going to use both of those forms, slope, intercept, and point slope. And we're going to do this problem twice, which seems a little strange, but I want you to see how you could use either equation to get the same sort of answer. It says, write an equation for the line that passes through the points 7, 2, and 0, 6. So you'll notice in both forms, we need to figure out what the slope is. So we might as well just start a nice slope formula right away. y2 minus y1 over x2 minus x1. Looks like our slope is negative 4/7. By the way, that negative could go with the 7, could go with the 4, or we could stick it out in front. So now that we know the m, how could we use this equation to finish it off? Well, in order to finish this problem, we would need to know what b is. So what we're going to do, oh wait, I think we know what b is, don't we? Isn't 0, 6 a y-intercept? It is. 0, 6 is on the y-axis. So we can actually just, if we were really clever, we could just write that down and be done. Now, if you weren't noticing that, if you weren't being that clever, what you could do is you could take the point 7, comma 2 and just temporarily plug it in for x and y in y equals mx plus b. So we would put the 2 in for y. Remember, our slope was negative 4/7, and our x value just temporarily is going to be 7. Add the 4 over and we get a b of 6, which we kind of already knew. That's what we had above here. Now, if you're feeling lazy, which sometimes I'm feeling lazy, I'm going to use point slope form. And as the name suggests, it's built for when you know a slope and a point. So, for example, I know this point and I know this slope. So what I could do is I could fill in just these 3 numbers, the x1, y1, and m. So y minus 2, which is our y value, equals m times x minus 7. That's a correct answer too. It doesn't look like this other one. We could make it look like the other one if we wanted to. Another way we could have done that, if we use this as our x1 and y1, we could have done y minus 6 equals negative 4/7 times x minus 0. That would be a correct answer too. How is it that there are 3 equations for just a single line? There's only one line that goes through 7, 2, and 0, 6. Can I show you a fun little trick? I'm just going to grab this guy. See, it turns out that all of these equations are actually the same equation. They're just written a little bit differently. Add the 2 over there. See, I told you. That's what we were looking at. So all of these equations are equations for the same line because they're technically all the same equation. They're just in different forms. Lesson 4 is linear functions, and there's a few different ways that we can think of functions. We're going to look at them as equations, as tables, and as graphs. So this first example is asking me to find what f of 7 equals. All that means is that the input number is 7. In other words, the x value is 7. So I'm going to put a 7 in wherever I see x. The f function is defined by an equation, so 3 times the x value minus 10. 3 times 7, 21 minus 10 would be 11. So the answer is 11, and by the way, that's a y value. So really evaluating these functions is just substituting in the input. If we were to look at a table, again, when the number is in the parentheses, we say that's g of 1. That's our input of 1. So when x equals 1, g of 1 would equal 7. So 7 is our output. 7 is our y value. And on the graph, just remembering again, this is h of x now. X equals 2. Well, here's where x equals 2 is. What we do is we line up where does x equal 2 match up to this function. That point is at 2 comma negative 5. And so when x is 2, y is negative 5. So when it's asking us to evaluate, it's just asking for y values. Now the way these last three are written, they're asking me what value of x will give me a y value of blank. So we're going to try that three different ways. Again, we're going to try it with an equation, a table, and a graph. Let's do the equation first. So here we want to know what f of x is. So f of x is 3x minus 10. I know that from up above. And I just want to know, when does 3x minus 10 wind up equaling 26? Well, that's just a cute little equation that I can solve. I'm going to add the 10. I'm going to divide the 3. And the answer is when x equals 12, the y value is 26. For the next one, I don't have an equation, I just have that table. So I have to understand that it's asking me for an input of x that would give me an output of 9. Here's where I'd be looking on that table. When x equals negative 1, g of x equals 9. Same thing on this last one. If you just are remembering that if I'm looking for an x value, that must mean they're giving me the y value. Here I'm looking for a y value that has 1. So if I follow that and I match up where it is on the function, I see that we've got a point at negative 4 comma 1. That's the x value, right? X equals negative 4 matches up to a y value or an output of 1. We've already been doing a little bit of equation solving, but lesson 5 is solving linear equations and inequalities. So I'm going to maybe write out some more steps than I normally would. When you first learned to solve equations, you would draw a line down and you would make sure that you showed what you were doing to both sides, always doing the same thing to both sides. I would not expect that you would have to write the things that I'm writing in black right now. That is optional. If you think it helps you keep track of what you're doing, that's fine. But I would want, when I say to show your work, I would want to see the work that's in orange here. And that's usually the work that I'm going to show. So x equals 3 is the solution to that first equation. You want to watch out on the second one. If you have x's on two different sides, that means you're going to want to combine your like terms first. You're going to want to get both x's to one side. You could go either way. I'm kind of a fan of subtracting the 3x, only because I like my x to come out positive. But you could subtract the 5x and we would get the same answer in the end. Then I'll be subtracting 11. And dividing the 2. And I wind up with x equals negative 2. You'll notice I did a little flipperoo there at the bottom. Technically, if I had more room, it should have been negative 2 equals x. Well, when it's an equation, you can flip those sides, and that's no problem. If you hit an inequality, same rules apply. On this one, it has some extra stuff going on. Why don't we just go ahead and combine some like terms before we even start? Those are on the same side anyway, so I can go ahead and do that subtraction. How do I get rid of the 9? I would subtract it, because it's a positive 9, so I'm going to subtract it to make it go away. And now I'm going to divide the -2. Do you remember? Do you remember? When you multiply or divide by a negative number, you reverse the inequality symbol. So that's really the only trick if it's an inequality versus an inequation. We'll try another one. This one has x's on both sides again. So if I'm following my usual pattern, I'm going to subtract the x over on this side. That would leave me with just the -6. We only switch the sign if I'm multiplying or dividing by a negative, so no need to switch here. And then what is 5x minus x? Think of that as 5x minus 1x is 4x. I'm about to divide both sides by 4. Only switch the sign if I'm multiplying or dividing by a negative. So I'm not dividing by a negative. So I'm just going to leave this as -13/4. Totally fine. So that would be an awesome answer, but I actually prefer my x's to come first. So if I'm going to rewrite this, this one says that -13/4 is smaller than x, which means that x is bigger than -13/4. Remember, on an equation, it didn't matter, but on an inequality, if you're going to flip it so the x is on the other side, you have to think about that inequality just a little harder. Lesson 6 is solving equations by clearing fractions, and this is where we just use our wits to try to kill these fractions. Do you see that 1/4 and that 2/3? If I wanted to add those together, combine like terms, I would need a common denominator. And that seems like a lot of work. So instead of getting a common denominator, which totally would work, there's this technique that a lot of algebra people use, and it's called clearing the fractions. If you were to get a common denominator with a 4 and a 3, what do both of those numbers go into? 12? 12 would be a nice common denominator, but instead of working with 12 as a common denominator, I'm going to use the 12 and multiply both sides by 12. On this side, I might want to think of it as 12 over 1 because I'm multiplying fractions. I know this seems like it's going to be more complicated, but watch, just watch. So we're going to have to distribute that to both of these fractions. When you multiply fractions, you multiply straight across. So you're going to multiply the tops together and multiply the bottoms together. 10 times 12. And I know this doesn't look better, but if you chose the right number, like 12, both of these should reduce to a whole number. What's 12 divided by 4? 24 divided by 3. And that's what I mean by killing the fractions or clearing the fractions. 3x plus 8x. And divide the 11 over. I'm fine with you leaving your answers like that. Next example. Sometimes the hardest thing is deciding what to multiply both sides by. We know to clear the fractions, we want to multiply it by something that divides nicely by 8 and by 12. What's 12 times 8? Like 96? That would work. 96 would certainly work. But I like to I want to come up with the smallest number if I can. I'm going to get the same answer no matter what, but I just want to keep the numbers small if I can. I think an 8 and a 12 would both go into 24, don't they? Like I said, 8 times 12 is 96. I totally could have used that. But if I can come up with a smaller number, it'll just keep my numbers smaller. Remember to multiply both sides by that clearing the fraction number. And we're going to multiply straight across. 24 times 3, whatever that is, and 1 times 8. 24 times 2. Over here, 24 times 5, whatever that is, over 12. And 24. You'll notice I didn't bother figuring out what 24 times 3 was because I knew that I would be able to reduce this fraction right away anyway. What's 24 over 8 reduced to? 3 over 1? Same thing over here. What is 24 over 12 reduced to? 2 over 1. Let's see if we can write that a little more simply. So we've got the 3 times 3 here now. That's a 9x. And now we've got the 2 times 5 up there. If there's just a 1 on the bottom, I don't need to write it. And the fractions are cleared. I'm going to subtract that 9x over. 10x minus 9x is 1x. And if I add 24 to both sides, what is that? 72. And we have a winner. And the last lesson in Module 1 is called Applying Linear Functions. It's basically understanding what y equals mx plus b is in terms of a real problem. Adam types 45 words per minute. At the beginning of the period, he has 280 words of his paper written. Write a linear function f of x that gives the number of words he will have written after x minutes of class. So the big things to know is that we know that m is our slope, that's our rise over run, but if you apply labels to that, a rise over run always has a word like per in it. So rise per run, words per minute. So if you can find that rate of change in there, you will have identified the slope. And since he's typing 45 more words each minute, that's a positive 45. And then the y-intercept is like when x equals 0. It means like when you start out. And when we started out this period, he had 280 words already typed. And so we just have to make a function. We're going to use that function notation. So instead of y equals mx plus b, just write f of x equals mx plus b. That's all there is to it. Let's try another one. Belinda spends $40 each day on her vacation. On the 5th day, she has $120 left. Write a linear function that gives the amount of money Belinda has after X days of vacation. Do you see a rate of change? A per? It doesn't actually say the word per anywhere, but it does say that she's spending $40 each day. That's kind of like $40 per day. Also, since she's spending that much, that's going to be a negative slope. She's going down by $40 every day, down by $40 every day. And they actually didn't tell us how much she started with, right? They told us by day 5, she was down to $120. They basically gave us an ordered pair. Do you remember how to handle that? How are we going to go back and backtrack and figure out how much money she had on day 0? You totally could just use your logic or your backwards counting or whatever. I'm going to do it sort of the algebra way. I'm going to plug in the y value I know, the slope that I know, the x value that I know, and I'm going to backtrack to find the b that way. So it's looking like she started out with $320 and she's down to $120 after 5 days. So I think I've got my function f of x equals negative 40 per day plus 320 is where she began. A nice way to check that is if you plug in a 5 now for x, negative 40 times 5 plus 320, negative 200 plus 320. That is $120, and that's what we were supposed to have after 5 days.